Test. Right, so good afternoon everyone. As you can see on the screen, I have uploaded the past year quiz 1 in Excite for you to have a practice, okay, on what questions you can you expect from the quiz. Okay, so I will not be uploading the solutions. Why? Because you can check the solutions easily. Okay, how you check? You can, of course, substitute back your solution into the problem and see if it's equal. Okay, so for example, if I ask you to find the eigenvector of a matrix, so what you do is that you get your eigenvector, then you take your matrix multiplied by the eigenvector, and you see if you can get a multiple times that same eigenvector. Okay, so therefore you can check easily. You can also make use of generative AI to check, okay, which are the correct solutions. Okay, but that is if you trust that the generative AI is correct. Okay, so therefore I will not provide answers. You can verify them yourselves. So now we are going to go through tutorial 2, right? Okay, question 1. Do I need to do? The answer is for the single matrix D that will perform all of these linear transformations in this order. So it must be like followed, it must be like scale up by k times first, followed by the rotation, then followed by the reflection. Okay, if you can do A, B, C, right, then you should be able to do D, matrix D. Do I need to go through? Huh? Yes or no? Okay. So matrix A should be obvious, right? Because you need to scale up by k times, right? So scale up by k times means you just have a diagonal matrix where the diagonal entries are k. Okay, the reason is because, right, you have to scale up the I and j vector accordingly by the same scalar magnitude, so that you can scale up the entire vector space by k times. Okay, so if you recall our lecture example, right, there's one that we scale up, I think, by 3 times. Okay, so there will be a 3, 3 here. But then if you scale up by k times, then you just have a kk there. Okay, so I think matrix A is quite straightforward, I believe. Then matrix B maybe not so straightforward. Okay, because this one rotate counterclockwise by angle theta. So because it's rotating counterclockwise by angle theta, so maybe it will be beneficial if we draw the 2D plane to see what we mean by rotating counterclockwise by angle theta. Okay? So what this means is that your input vectors, so your input vectors will be I and j, right? But if you rotate counterclockwise by theta, that means the output vector must be like I rotated by theta. Okay? Then after that you have j rotated by theta, and this is theta. Okay, so these two are the output vectors of your linear transformation. Okay, because you rotate counterclockwise, what? Right? By angle theta. Right? So I becomes this green vector, and then your j becomes the red vector. Okay, of course with no change in the length or the magnitude. But if you understand this, then actually you can write down the matrix B already. So the matrix B must be what? So what is the I component of the green vector? The I component must be cosine theta, what? Correct or not? So therefore this will be cosine theta. Okay, because that's the x component. The x component, right? What I'm trying to say is that the x component is the component that is here. Okay, this component. Okay, maybe let me use a different color. Can you see? This is the x component of the green vector, right? So therefore it must be cosine theta. Then what is the j component? J component is the one that is on the y-axis, right, of this green vector. So therefore it must be sine theta. Okay? So the j component, let me use a different color here, which is this component. Okay, so you can see the projections, right, on the x and y axis respectively, those are the components of your output vector when I is being rotated. Okay, when vector I is being rotated. Then you just do the same for your j vector. Okay, so the j vector will be what? You can see that this is what? Minus sine theta. Why minus? Because it's on the negative x-axis. Then the vertical component of the j vector being rotated, right, will clearly be cosine theta. So this will be your matrix B. Any objections? How do I get? Okay, so you see, your columns of your linear transformation matrix, right, will be the output vector when you transform I and j respectively. Okay? So therefore, what is the output vector here? When I say output vector, right, so you can see this green vector, okay, it is a rotation of the input vector I. So originally, let's say this is your I vector. Because your output vector must be such that it is rotated counterclockwise by angle theta, ma? Correct or not? So that means that this I vector must be rotated to the green vector here. Okay? The magnitude will still be 1, right? Because the length of the unit vector here is 1. Okay? So then, let me remove that. Then, you ask, what is this vector? How would you denote this vector? A 2D vector, it must be x component and y component, what? So therefore, the x component must be this vector cosine theta. Correct or not? Then, what about the y component? The y component must be this vector sine theta. So you get a pink color one. Okay? So therefore, x component, y component, you get cosine theta and sine theta respectively. Then you just repeat this approach for your j vector that has been rotated. Okay? Because you must remember, it says here that B has to rotate the vector space, right, counterclockwise by angle theta. So that means that the j vector now rotated by same angle theta. Then you ask, what is the I component? You can see on negative, okay, on the negative x-axis. So this is sine theta, the length, right, is sine theta. So therefore you have minus of sine theta. And take note that because theta is acute, right, so therefore you have to put a minus, okay, because if theta is acute, sine theta is positive. So therefore, you have to get a negative x component. Then the same goes with the y component of this vector. So lastly, reflection about the line y equals to x. Okay, so really to define the transformation matrix, what we do is just draw out the output vectors. Then after that, just write down the output vectors concatenated. That's all. Okay? So now you see that for matrix C, right, maybe I can also make a quick drawing. And then, so you can see that I must be reflected about the line y equals to x, right? But where is y equals to x? Y equals to x is just this line. But y equals to x, if you reflect I over y equals to x, then it becomes j, ma. Then if you reflect j over y equals to x, then it becomes I. So then this tells us matrix C. So matrix C must be, output vector here must be j, because I reflected to j. So that means it must be 1, 0. 0, 1. Then similarly, j vector gets reflected to I. So this must be 1, 0. So that defines your matrix C. Okay, it's a reflection matrix. Any questions on the approach here? Yeah, so if you have no objections with A, B, C, then after that we can write down the matrix D already. So matrix D, it says, right, you must have the transformations applied in this order. Okay, and take note that because matrix multiplication is not commutative, right, A times B not equals to B times A. So which means that the order of transformation matters. Okay, you cannot do like C first, then followed by B, followed by A, right, in order to get the same overall transformation. So in this case, the matrix D must be what? Because in this order, so in this order means what? In this order means you have to do A first, right? Then put A into B, then after that put B into C. Okay, so what that means is you want to have the linear transformation T of C of T of B of T of A of the vector space. Okay? So you can see here, you have to follow the order. A first. So do the T of A first. Do the transformation by matrix A first. Okay, then after that, take the result, put into matrix B. So this is what this is trying to say. Okay, you have to follow this order. And finally, take the result after transformation by matrix B into transformation by matrix C. That's the last one. Okay, so therefore, what is the end result? Well, the end result is really just C times B times A. Okay, so it's really just C times B times A. And you can see that, right? Okay, this is just a linear transformation applied to some vector space. Okay, so therefore let me just remove the vector or else I have to put dv. So let me just remove this vector. Okay, or maybe just put d times v here so that it becomes more general. Okay, so it's really CBA times v. Can see the T, the transformation by matrix A, right? It's just AV. Then after that you plug into linear transformation by matrix B, so it's usually B times this thing. Okay, then finally for C. So it's CBA, not ABC. Okay, if you think you follow this order, it's ABC, then you're wrong. So therefore, in this case, right, if you multiply out, then you'll be able to get the matrix D. Why is this CBA? You understand this part or not? This part you understand? Hey, this classroom like a bit hot, right? Wait, I want to call the help desk. Hold on, you're hanging there for a while because this one must call. Technical help desk should be correct. Just relax for a few minutes. Right. Okay, hopefully the heat get resolved fast. Okay, so why is it that it is CBA, not ABC? Because what is TA of V? What is this? This is A times V, what? This is just coming from your lecture notes. Can you see the linear transformation here? Right? T of V equals to AV. Right? Just a simple direct multiplication. So see here, T of A equals to AV. Right? Isn't that correct? Okay, then what is T of B of AV? Then, because T of B is just, this guy, is just B times whatever you put in. Correct or not? So it's actually B times AV. Isn't this legit? Then T of C equals to CV. Right? So therefore this T of C is just C. Just take matrix C, multiply by whatever you put in. So it must be CBA. Is that right? Okay, so which means if you put in any vector as part of the vector space, right, you must go through matrix A first. Then take the result, put inside the transformation by matrix B, and repeat that for matrix C. Can? So therefore, in this respect, the matrix D, right, must be CBA. Okay? So D equals to CBA. So if you calculate this on your own, everything has been given here, you are going to get this answer. So this one you DIY, just matrix multiplication. Is that right? Okay, good. Question 2. I don't think I need to do, right? Do I need to do any of the parts of question 2? Just solving by row operations. Okay, good. So this one DIY. Question 3. For what values of P this element is matrix B not invertible? So you'll get P equals to 3 by putting the determinant of matrix B to be 0. Okay, so you just solve for the determinant of B, put it to be 0, and then solve for P. Because it's just one equation, one unknown. Do I need to do? Yeah, because you want values of P for which B is not invertible, right? So cannot be inverted. Cannot be inverted means, right, the determinant must be 0. Okay? So you should be able to solve for the 3 by 3 matrix determinant. Okay? So this one DIY. Question 4. Determine the inverse of the following matrices exists and find the inverses if they exist. So A inverse exists, B inverse doesn't exist, C inverse exists as well. So this one, do I need to do any of them? No need? Good. Okay, this one DIY. Question 5. Find the eigenvalues and eigenvectors for the 5 matrices here. Do I need to do any? Yeah. Okay, so maybe I'll do E, right, and explain why is it that the answer is written as such. Okay, because E, right, is a pure scaling matrix. So the deal with the pure scaling matrix is that if you notice the pure scaling matrix, in this case 4, 4, right, at the diagonals. So you notice that your I vector and your j vector, the linear transformation just scales up the two vectors by 4 times. So maybe something like that. Okay, so that's all. This guy is 4, 0, and this happens to the j vector as well. So this guy will be 0, 4. Okay, so therefore, original vector space, which is this unit square here, right, has been scaled up like 16 times on the area. Okay, but the lengths are scaled up 4 times each. So if you were to take this, multiply by any vector, that means linear transform any vector. So let's say, for example, this vector. Now this vector, after you scale, after you multiply by this, right, is going to get scaled up 4 times as well. You notice that? Okay. So this is also evident, right? That means any vector you multiply by E is just going to get scaled up. Okay? 4 times longer. And this is also evident if you take E, right, and rewrite it. Okay, so E times any vector V is equivalent to 4 times I times V ma. Okay, now because if you factorize out the 4 here, right, then it's just 4I. So this guy is really just 4I. 4 times 1, 0, 0, 1. But 4IV is just 4V, right? Because I times V will just give you V. So you notice that all vectors V are eigenvectors. Because it results in E times V equals to 4V, then 4 is the eigenvalue. So this guy is the lambda. Okay, this guy is the eigenvalue, right? So therefore we can say that, right, all vectors V are eigenvectors. Okay, so how do we denote this? So that means we can write V equals to AB for all. So this is for all. Okay, so for all, A is an element of all real numbers, comma, B is an element of all real numbers, provided that they are not 0. Okay, cannot be 0. So if I write like that, right, it means all real numbers but cannot be 0. Okay, because 0 is the trivial solution. We don't want that. We want our eigenvectors to be non-zero vectors. Okay, and with the condition that, right, because you have V1, V2 ma, so therefore V1 and V2 cannot be parallel because you want 2 eigenvectors since this is a 2 by 2 matrix. So if you put V1, comma 2, right? So then you have to also put in the condition V1 not parallel to V2. Okay? So then this will be your complete solution. So if you were to choose any 2 eigenvectors, you can just choose like 1, 0 and 0, 1 or any other 2 non-parallel eigenvectors. Okay? And in this case, notice that the eigenvalue is just one eigenvalue of 4. Okay? And indeed, you can of course solve the characteristic equation, right? You do lambda square minus the trace, which is 8. So therefore you get lambda square minus 8 lambda plus 16. 4 times 4 is 16, right? So therefore the repeated eigenvalue is 4. Okay? So you notice that what I'm trying to say here is this, if you do the long-winded way, okay, so lambda square minus the trace, right, which is 8 lambda plus the determinant. So the determinant is 16. Then this guy is equivalent to 0. Then you notice that you get lambda minus 4 square equals to 0. So therefore you get lambda equals to 4. You only have one eigenvalue. Then in this case, for this particular eigenvalue, the algebraic multiplicity is 2, because the power here is 2. Okay, then at this juncture, maybe you think that, oh, this one 2 but then it is possible that it doesn't give me enough eigenvectors. Okay, but if you look at the condition here, you're going to realize that when you try to solve for eigenvectors, right, E minus lambda I times V equals to, so if you minus lambda I, what do you get? You get 0, 0, 0, 0 times xy equals to the 0 vector. Then what does this tell you? X and y can be anything, right? 0 times x plus 0 times y equals to 0, self-fulfilled already. So what does this tell you? X and y can be anything. X and y can be anything. Okay, there's no constraint at all. Now, if x and y can be anything, what is the eigenspace? The eigenspace is the whole plane, because the whole plane represents all values of x and y. So the eigenspace is the whole 2D plane. So because the eigenspace is the whole 2D plane, since x and y can be anything, right? So therefore, the GM is 2. Okay, so geometric multiplicity equals the algebraic multiplicity. So hence, is E diagonalizable? The answer is yes. You can choose any convenient 2 eigenvectors. Okay, so for example, right, if I want to diagonalize this, right, eigen decomposition, so therefore I can just conveniently choose V1 equals to 1, 0, V2 equals to 1, 1. 0, 1. 1, 1 also can, but just a bit more tedious. Okay, so if I want to put E equals to PDP inverse, what do you realize? This is 1, 0, 0, 1, right? But this is what? This is I, identity, right? 1, 0, 0, 1. Then your D is 4, 4, 0, 0. Then your P inverse, of course, is I inverse. So therefore, it's 1, 0, 0, 1 inverse, which is still 1, 0, 0, 1. So therefore, this is what? This is telling you that PDP inverse is ID I inverse. Okay, because I inverse is still I. But the diagonal matrix is E itself, because E itself is a diagonal matrix. Okay? So what I'm trying to say here is that if you have a pure scaling matrix, then you can basically choose any eigenvector, any convenient eigenvector. So the most convenient one will be the unit vectors I and j, or ijk if you have a 3 by 3 matrix. Okay? And because this is really diagonal, so when you do diagonalization, what would you expect? You expect to get back the same matrix. E equals to dy. Isn't that correct? Because E itself is already a diagonal matrix. So you'll be expecting to get the P matrices, the P matrix as an I matrix. Any questions? Okay, good. So that will be for part E. And the rest, I think I don't need to do, right? Okay. So this is done. Right, so basically this one is just telling you that V1 not parallel to V2. Okay, so V1 cannot be a constant multiple times V2. So it's saying that not parallel. Okay, so that's question 5. So it's done. So normal. Just a little bit. Thank you.
Because more people are some
Okay. Thank you. Right, so question 6. Attempt to diagonalize ABC, right? Wait, let me see, blah, blah, blah. Oh, okay, so ABC, all diagonalizable, as you can see from the answers given. But I suppose I will need to go through C, am I right? Okay, wait, okay, this one you DIY. So this one you DIY, this one DIY. So I'll go through C. Right, so for matrix C, if you try to solve for the eigenvalues, lambda square minus the trace, but the trace is 0, right? So it's lambda square minus 0 lambda plus the determinant, right, which is minus 4 plus 5. So it's plus 1. So obviously, if you put this to 0, you are getting lambda square plus 1 equals to 0. That means lambda square equals to minus 1. So that means lambda equals to plus minus I. Okay? So of course I can say that lambda 1 equals to I, lambda 2 equals to minus I. So I found the two eigenvalues, they are imaginary, which means in this particular matrix, the linear transformation will make sure that all vectors get rotated. All vectors will get rotated. That means you cannot possibly find any vector when multiplied by matrix C, right, doesn't undergo any rotation. So therefore, no real eigenvectors. Okay, so this means no real eigenvectors. Okay, but even though there are no real eigenvectors, we can still proceed on to find the imaginary eigenvectors. Okay, actually they are more generally complex eigenvectors. Okay, so therefore let's look at how we can solve this. So you can C minus lambda I. Right, so we have lambda 1 first. Okay, I'll solve for lambda 1 first. Then lambda 2 actually no need to solve. Lambda 2 we just make a manipulation will do. Okay, I'll show you in a bit. So C minus lambda 1I times V1 equals to the 0 vector. Oh, by the way, when you, okay, this one later I'll say. So now, from here, right, you're getting C minus, okay, so this is what, I, right? So it's 2 minus I. 2 minus I minus 5, 1 minus 2 minus I times xy equals to the 0 vector. Can Okay. So then this gives us a kind of a new problem, because so far when you solve for the real eigenvectors, right, the two rows will usually be dependent. So now, but if you look at the two rows here, it doesn't look like they are dependent, because this one minus 5, what? This is 1, right? So it doesn't look like they are dependent, but they are dependent. I'll show you in a while. Okay? So let me solve for the eigenvector first. So I like the 1, I don't like the 5. So I'm going to solve from second row. Okay? So second row is going to give me x. Then we have minus 2 plus I times y equals to the 0. Okay? The bottom 0 in the 0 vector. Can second row. Okay, x. Then after that minus. Then this factorize out the minus here. So become 2 plus I times y, right? Equals to 0. Okay? So let me show you. So y, or rather I can say that x equals to 2 plus I, y. So this is the span. The span in the complex space. Okay, so which means, right, I can say that choose V1 to be, so you just set your y to be 1, and then your x must be 2 plus I. Okay, so this can be an eigenvector V1. But as I mentioned, eigenvector is not unique, what? Correct or not? You can choose your preference. Then some of you may say that, oh, okay, I can work from the first row. The answer is yes, you can also work from the first row. So so I'm going to put an or here, okay, just to show you another variation. So or, it can be 2 minus I times x minus 5 times y equals to 0. So in this respect, you can get y equals to 1/5 of 2 minus I times x. So therefore, you can also choose V1. So if you put your x as 5, then 2 minus I will be at the y component. Okay, I just choose x as 5 because I don't want to have the fraction. So therefore, 5 times 1/5, right? I'm going to get 2 minus I. So this is also legit. Is that right? Okay, then that begs the question, right? A, is this the same span as this or not? Because if it's not the same span, then we're in trouble. Okay? Because it is expected that the one eigenvalue here must give us only one eigenvector. Okay? Because the other eigenvalue is expected to give us the other eigenvector. Right? You shouldn't have more eigenvectors than the column space of the matrix. So therefore, can we check or not? Are they along the same span? The answer is yes, yes. Okay, it's not difficult to check. So let me just do a quick check here. This one optional, this one optional. Okay, so from here, check if same span as this guy. Okay, how to check? Just isolate. This guy is isolating y ma, but then this one isolating x. So what you do? This one isolate x lah. Very simple, just isolate x. Okay, so how do you isolate x? You just multiply by the conjugate, because you want to get rid of the imaginary here. Okay, so therefore from here, multiply by the conjugate. So multiply by, multiply by 2 plus I. So if you multiply this by 2 plus I, then you get a 2 plus I y. Then this is equivalent to 1/5 multiplied by 2 plus I times 2 minus I x. Okay? So therefore you can see on the right hand side, right, you're going to multiply out. So you get 1/5, right? Then this will give me 4 minus I square. But I square is just minus 1, what? So therefore this is 1/5 times 5. 4 plus 1, x. So therefore this is just 5 divided by 5. So that gives x. Okay, so you can see x equals to 2 plus iy. It's exactly the same span. Okay, so which means that if you were to have substituted your eigenvalues in correctly in the eigenvector equation, then you can just conveniently choose any of the rows to solve for your V1. Okay, so all these are optional. Maybe I just make this part no need to do. I just show you that you can use any of the rows. Okay, so now do I need to solve for V2 or not? Actually no need. The reason is because V2 is minus I ma, correct or not? It's minus I. So therefore you will realize that if you solve for V2, right, it will be the complex conjugate of V1. So let me quickly show it to you. Okay, so for V2, this one just remove. Make it become lambda 2 V2 for V2. Okay, so now you see, you get this guy. But this guy, the I become minus I, correct or not? So let me move I a little bit towards the right. So let me put a minus. Okay, this one is like minus I. Okay, wait. Okay, let me put a minus in, then you see how the minus get. Okay, wait, let me choose a nicer color. Okay, this one is a minus. Minus I, minus I. Okay? But then the minus I will carry forward, ma. Correct or not? So this minus I carry forward to the span equation. Okay, I copy this whole thing, then you will see. Okay? So you can see the minus I gets carried forward to this part. Okay, wait, I change the plus to minus. Okay, this is minus I. But if this is minus, then this must be minus. Then if this is minus, then this must be minus. Okay? So what I'm trying to say here is this. The minus I will carry itself forward into the span. Okay? So what's going to happen is this. V2 is going to be the complex conjugate of V1 and vice versa. Okay? So you notice that V1, right? V1 will be 2, 1 plus I0 plus 1, 0 times I. That's V1. Can you see V1? Okay, 2, 1 plus 1, 0 times I ma. Correct or not? Then V2 will always be 2, 1 plus, minus 1, 0 times I. So the relationship here is the plus become minus. Always like that. Okay, so these two are conjugates. So what I'm trying to say here is that, right, you don't even need to redo the whole process. After you found V1, right, after you found this V1, right, you just make the plus I become minus I, then that's your V2 already. Simple as that. Okay? So complex conjugates so V2 can be directly stated after V1 is found. No need to go through the whole process again. Any questions? Yes? Your question is V2 going in the opposite direction of V1? Ah? Oh. Okay, you must understand that, right? This is a complex vector. Okay, because it's a real part and it's an imaginary part, right? Okay, it's a complex vector, it's not the normal vector. So therefore, in this respect, you cannot show this on the 2D plane. You cannot show this on the 2D plane. Can you show this on the 3D space? The answer is yes. Okay, so the xy plane can represent for the real part of the vector. Okay, then after that you need to have another plane that is in the complex plane. So the complex plane can be treated as like a orthogonal to the xy plane. So it's overall like a 3-dimensional space to show a complex vector. Is that alright? Okay, so therefore it's more like that lah. So let's say if this is V1, that means it has a real component and an imaginary component. Then the V2 must be reflected about the xy plane. Is that alright? Okay, but the whole complex so-called vector space is a 3-dimensional vector space. It's a 3-dimensional space. Okay, so we got to answer the question. Okay, and this is something that I want to like put it down. Okay, because I think I mentioned it during lecture, but I didn't exactly put it down. Because some of you came to ask me. Okay, so the diagonal form must be PDP inverse, but you must strictly follow the order of your eigenvectors to that for the eigenvalues. So if your P, you put down V1, V2, then the diagonal you must have lambda 1, lambda 2. Must be strictly in this order. If you put V2, V1, that means you swap V1 and V2, right? Then you must also swap lambda 1 and lambda 2. Okay, that means you cannot anyhow like plug the eigenvectors in whichever order that is different from the eigenvalues. That is the main takeaway. Okay, so therefore this will be 2 plus I1 and this is 2 minus I1. Then this one must be I minus I. Okay, then this part you can work out P inverse. Did I give you P inverse? Yes, I did. So the determinant you can find. You can see that it is this times this minus this times this. Okay, so it's really just 2 plus I minus 2 minus I. Right? So hence I get 2I. So it's 1 over 2I. Then multiply by 1, 2 plus I. And throwing a minus to the off diagonals. So I minus 2. Okay, I better put down the thing here. Any objections? Order must be equivalent. If you messed up, then of course you will not get the original matrix C when you multiply out. Okay? So you can see for complex eigenvectors, maybe a little bit tedious, but it's perfectly doable. Okay, so the rest of question 6, I'll leave it to you. Can Right, so question 7, do I need to do? Basically diagonalize and then compute the two functions there. Do I need to do question 7? Yes? Okay, I think the diagonalizing part I no need to do, right? No need to do, right? Diagonalizing part. I just write down the PDP inverse first. Then after that, right, I will show you how you get the functions here. Okay, the result here. Can Okay, wait. Okay, wait, let me see. Okay, so this part you DIY. So A equals to PDP inverse. So let me check my solutions. Hey, wait, is this covered previously? Nope. Okay, hold on. Let me look at my solutions last year. Okay, crap, I also didn't do last year. Anyone did already or not? Give me the P and D. Anyone done already or not? I believe there will be some very enthusiastic students here. Seriously? No? Never do Okay, you do now. Do now. Then I mark attendance. Then after that, I'll show you how to get the solutions. Okay, do now. Alexander, Ballard, Aliyah, Emelina, Emelina? Hey, I thought she's here in the morning. Went back Angelico, Sean, Brian, Chen Chang, no. Chen Yi, Ivan Chow, Yang Ing. Yang Ing also went back Okay. Emilia, are we not here? Yan Jing, Zhan Yang, Dongbin, Noritetsu, Xavier, Joey went back. Jordan, Kyla, Kevin, Ken Leong, Charan, Dawson here or not? Okay. Chen Ying, yeah. Chen Ying here or not? Jonathan, no Jonathan. Kun Yong, Mac, Mikhail, Mohan, Azari, Danish, Afan, Naya, Bingjie, King Hong, Toilet Zixuan, Fadila, Phoebe, Yan Heng, Sherwin, Benjamin, Raymond, Reese here or not? Rujira Tanalai, Jumpang, Jerome, Sean, Justin, Hapo, Ryan, Sohadi, Johans, Weiyan, Yi Chong, Kemzen, Trisha, Hong Tan, Shikang, Xingzi, Zotet, Zunping Wai. Anyone got P? No? Thank you. 1/8. Yeah, correct. Okay, thank you. Yeah, so do you get the values here? Eigenvalues will be -2 and 6 respectively. Then the eigenvectors are here. Can So, how do we get this a to the power of 5 plus 7, a to the power of 4 plus I? Okay, so it's really just making use of the diagonalized form because A is PDP inverse. So the first one is P times D to the 5, right, times P inverse. Then this is plus 7 D times P times D to the 4 times P inverse plus this I, you can write it as PIP inverse, okay? Because PIP inverse is also I what? Legit, right? Can So therefore, the reason to write this way is such that you can factorize out the P at the front. So it's P times D to the power of 4 plus 7D to the power of, wait, this one is D to the power of 5. Then 7D to the power of 4 plus I times P inverse, okay? Then actually in the central part here, you just need to apply the power to the eigenvalues. So D to the power of 5 will be minus 2 to the power of 5. So this is minus 2, right, to the power of 5, plus, then the other one is 7 times minus 2 to the power of 4, then plus 1, because you have an I here. Okay, I will have a 1 at the diagonal. Then the same goes with the other eigenvalue, 6. So it will be 6 to the power of 5, plus 7 times 6 to the power of 4, plus 1. Then this one P inverse. Okay, because your P and P inverse already calculated, what? Correct not? So therefore, this can be calculated to give you the answer here. So I'll leave you to double check this on your own. So this one, after you multiply out, you will get the given answer. So this one is 6369 6288. So that's for the first part. Okay, then compute this if it exists. Why is it that there's a if it exists? Because it might not exist. Okay, the reason is because you have to look at your eigenvalues. Okay, if your eigenvalues, right, when you try to take the root, oops, this is minus 2 and 6, I think that's correct. 5 plus 8, oh, okay, there's a 5 there, so that's fine. Okay, so this one, the root of 5i plus a. So basically you just make use of the diagonalized form also. Okay, so it'll be what? It'll be root, so it's basically power half. Okay, so therefore what is this? This is the root of 5 times PIP inverse PIP inverse plus PDP inverse. So this is equivalent to, okay? So whatever function you do, you just do to the diagonal. So P can be factorized out. So this becomes root of 5i plus D, P inverse. So then the root you just apply to the diagonal elements. So this one must be a root of what? Of 5 times I, which is 5, plus D. So lambda 1 is minus 2. So it's 5 minus 2. Then the other one will be root 5 plus 6. Is that right? So therefore, this guy will be this. Therefore, you see a root 3 and root 11 right there. Okay? So those are the two elements here. Any questions? Negative 6 and 2. Should be minus 2 and minus 12. Maybe you're missing a minus. Okay. Minus 12. Minus 12 is 4. Wait, this should be minus 2. Is it minus 4, right? Or it should be the trace that is negative. Minus the trace.
Okay.
Not plus trace. Correct? Any other questions? Okay, good. So this is done. Okay, let me see. Okay, I think we have too many problems. So I think we take a break. Let's take a short break before we continue. Okay, 3:25. Okay, continue. We are a bit short on the time. Okay, so question 8. Question 8 actually nothing much, right? So you can see the answer, basically just apply the same function of the matrix to the eigenvalues. Okay? So then, truth is, right, are there any restrictions on the eigenvalues for the matrix functions to be defined? So psi A has no restriction, okay, because the eigenvalues here can be anything. Okay, so for psi A, right, no restriction, because you can always sign any real number. Okay, but then ln, there will be a restriction because you want to ln the individual eigenvalues. Okay, so in order for the ln of A to be defined, it implies that the ln of the eigenvalues must be defined. And ln is only defined for what? For positive values of the eigenvalues. Okay, so this ln A, right, will be defined for all lambda more than 0. Okay, so it must be defined such that it is only defined if all your eigenvalues are positive. Okay, because you cannot ln 0 or ln a negative number. Yep. Yeah, different functions might have, for certain functions there might be some restrictions. Okay. Okay, I think question 9 and 10 and 11 very similar. So I'll just choose one to do and then leave you to DIY on the rest. Okay, let me see the answers. Okay, I'll do question 11. Okay, this one DIY. Question 10 DIY. But then I'll do question 11. Okay, because question 11 more interesting. First of all, if you are tasked to show that any given vector is an eigenvector, okay, there's no need to go through the whole process of finding eigenvalues and followed by eigenvectors, right, to prove it, because that's a bit taking too much time. Okay, so what you do is just take A multiplied by V will do. Okay, because you just need to show what, right? Show only. So therefore, to show, you really just do AV. So just take A times V1. Okay, then you take this matrix times V1. So that's going to give you, so you straight away calculate. So it will be minus 5 times 2. Okay, so let me write down the arithmetic first before I make mistakes. So it's minus 10 minus 16 plus 32. Then there will be a 4 minus 2 minus 8. Finally, it will be minus 4 minus 4 plus 11. So just multiply out will do. Okay? So therefore this is what? Minus 26 plus 32. So that's a 6. Then this is 4 minus 2 minus 8, right? So therefore it's a minus 6. Then the final row will be minus 8 plus 11. That looks like a 3. Okay? Then what do you realize? Isn't 6 minus 6 3? 3 times of V1. Agree, huh? Okay, you just take 3 multiplied by V1, you get this factor here. So what does that imply? That implies that V1 is an eigenvector. Okay, because it's just lambda 1 V1, what? Any objections? So that's the showing part. Okay, so you really just need to see if you can satisfy the eigenvector equation. AV equals to lambda V. No problem, huh? Okay, next up, we'll be finding other eigenvectors. So the finding of other eigenvectors, right, you will need to painstakingly go through the process. Okay, so which means the determinant, there's no shortcut that can be used here. The determinant of A minus lambda I, set it to 0. Okay, but the determinant of A minus lambda I, right, will be minus 5 minus lambda, 1 minus lambda, 11 minus lambda. So this is a big hassle because you don't have any zeros. Okay, so you can just choose any of the rows or any of the columns, right, to multiply out. Okay, so maybe I'm going to choose the first row. So it will be minus 5 minus lambda multiplied by 1 minus lambda, 11 minus lambda, minus, or rather plus 16, then minus 8. 2 times 11 minus lambda, minus 16, finally plus 32, then multiply by 4 minus, or rather plus 2 times 1 minus lambda. Okay, so you can see that this, if you go and work out the arithmetic, you'll get a cubic equation in lambda. Let me get it out. Where is it? Okay, this one I'll fill in later before I upload. Okay, then equal to 0. Okay, what's important here is that you get lambda 1 equals to 3. So I can say that lambda 1, 2 equals to 3. So in this cubic equation, right, if I were to solve the cubic equation using a calculator, okay, I will get lambda 1, 2 equals to 3. That means there is a repeated eigenvalue with algebraic multiplicity of 2. Okay, let me write AM equals to 2. Then the other one, it will be lambda 3 equals to 1. Okay, so this will be my eigenvalues after I solve this long equation, cubic equation. So then, notice that I already have one eigenvector, which is 6 minus 6, 3, right there. Okay, but I still need the other eigenvector because this is algebraic multiplicity equivalent to 2. Okay, so that means there is an eigenplane associated with this eigenvalue. So therefore now I need to solve. Okay, so for lambda 1, 2 equals to 3. So therefore I write A minus lambda 1, 2 times I. So let me solve for V. Okay, I put V first. Okay, let me put V first. So that will be equivalent to the 0 vector. Okay, maybe let me just straight away minus from there. So this will be minus 5 minus 3, right, which is minus 8. Then 1 minus 3, which is minus 2. 11 minus 3, you will get 8. So therefore this is 8, 32. 2 minus 8. And this is minus 2, 2. So you might observe that actually all three rows are dependent. Okay? You can observe that row 3 times minus 1, you get row 2. Correct? Times minus 1, you'll get exactly row 2. But then if you take row 3, right, times 4, you get row 1. So all three rows, they are dependent. So indeed, that is to be expected because your eigenspace is a plane. So if I were to, for example, take row 3, solve from row 3, right? Then I notice that I get minus 2x plus 2y plus 8z equals to 0. And there are no other constraints. No more constraints because all three rows dependent. Okay? So this is an eigenplane. Oh, sorry, this should be a 0, not 0 vector. Okay? This guy is an eigenplane. Eigenspace is a plane. Okay? Geometric multiplicity is 2. Okay, you cannot get any other further constraints really. Okay, so of course, this one, if you were to simplify, right, then you can get something like, for example, x equals to y plus 4z. Okay, x equals to y plus 4z. So, yes, it's 2 because this represents a plane. So, the dimension of the eigenspace, which is a plane, right, is 2. This is a 2D plane. That means it's a plane in 3 dimensions, but on the plane is only 2 dimensions. So because your x, y, z, they are not entirely free, you know. You only can choose, for example, if I write it in this form, right? If I choose my y and z, then the x is automatically defined. So at any one time, there are only 2 free variables. So that's also referring to the geometric multiplicity being 2. Okay? Yep. So if you look at this guy, you can choose 2 eigenvectors to span the plane. Okay, so choose V1. So but V1, right, is already 2 minus 2, 1 ma. So if you have 2 minus 2, 1, I mean there's no need to use this lah. Okay, you can choose your own V1, right? Because you can say that find other eigenvectors, right? And then you describe the eigenspace geometrically, then you diagonalize. Okay, whether you want to use V1 or not is up to your choice. Okay, but since I'm given, right, so might as well I use it. So you might observe that 2 minus 2, 1 exactly satisfy this what? Because if y is minus 2 and z is a 1, then obviously this is minus 2 plus 4, right? Minus 2 plus 4 will make x 2 what? So I can just choose V1 to be the given eigenvector. Then I just have to choose another one and V2. So make sure that V2 is not parallel to V1. Okay, so what could be another nice choice? Maybe a simple choice, right, will be z equals to 0, y equals to 1. So V2 can be 1, 1, 0. And choose z equals to 0, right, y equals to 1. Then your x must be 1, no choice already. Is that okay? Okay, so this is the part that maybe I want to go through with you just to make sure that whenever you get the eigenvalue am equals to 2, right, you should expect, if the question asks you to diagonalize, then you must expect gm equals to 2 as well. Okay? Otherwise, you have to use Jordan decomposition. But for 3 by 3, I will not test you, okay, in this module for Jordan decomposition. So Jordan decomposition, you just make sure you know until 2 by 2 matrix can already. Is that right? Can Okay, so, well, due to time constraints, right, for lambda 3 equals to 1, you DIY, okay? Then you will be able to write down the A equals to PDP inverse, okay? So this is the part that I want to cover with you. Any questions? Good. Okay, so this is for question 11. Question 12. Oh, sorry. Okay, question 12 is also the same type as the earlier question whereby the matrices are 2 by 2. Okay, so you just diagonalize. You can see a lot of zeros here, so quite nice to find the eigenvalues. Okay, then subsequently you need to do cosine B. Okay, so cosine B really just cosine the eigenvalues, then the P and P inverse, no change. So this one DIY. Okay, quite straightforward. Then Jordan decomposition. So this one I will leave you to DIY because I've gone through 2 examples in the lecture already. Okay, so Jordan decomposition only for 2 by 2 matrices. Can Okay, so this one nothing much. J equals to P inverse AP. So why is this so? This one is from A equals to PJP inverse. Because from A equals to the Jordan decomposed form, PJP inverse. So you can see that, right, if you multiply both sides by P inverse, so it's P inverse A, right, equals to J times P inverse. Then if you multiply by P on the right side, then this will give you J. Okay? So what you need to do, right, is that after you got the Jordan decomposed form, then what you do, right, is just take P inverse times A times P. You must get this J. Can Okay? So, for example, let me just let me just show you that. Okay, let's say you should get P inverse AP. So P inverse is this one. So 0, 4, 1, minus 4 times the matrix A. 1, 4, minus 4, minus 7 times P inverse 1, 0, 1 quarter 0. This one must give you the J matrix. So the J matrix will be minus 3, 0, 1, minus 3. Okay, so this is verification that your answer is correct. Okay, of course you can choose your preferred eigenvectors and generalized eigenvectors. May not be the same as mine. Okay? Okay, wait, let me see. Okay, I'll go through question 14 with you. And then I'm going to leave question 15 to after the quiz. Because question 15 will not be tested in the quiz. Okay, but this question 15 is a past year paper, right? So I should go through during our following tutorial. Okay, perhaps on Monday after the quiz or on Tuesday. So, but now I will end today's lesson with question 14. Okay? So what's the deal with question 14 here? Because it looks a bit funky. Okay, it says here, without solving for eigenvalues and eigenvectors, show that the matrix B is defective. That means you don't even need to solve. You will know that it's defective already. Huh? Why? That means you don't even need to look at the eigenvalues and vectors. You just one look at it, right? You know it's defective. This one? What about the one here? Should be 0? No. Matrix B can be any matrix, what? How can I tell that this matrix is really defective without looking at the comparison of the AM and GM of the eigenvalues? The determinant is 0. No, the determinant is 4. 2 times 2 minus 0 times 1. What? So the determinant is not 0. It's invertible, matrix B. Huh? What is the deal with this matrix such that I can easily or immediately identify that it is defective? Any guesses? Any other guesses? No? Huh? Then, okay, matrix B is defective because itself is J. Itself is J. Didn't you realize? This is J, what? J is lambda, lambda, 1, 0. Always like that. Okay? So therefore, since B equals to J, but when this is equals to J, it is also equivalent to PJ P inverse, where P must be I. Okay? B is defective. Okay? Yeah. So you can immediately recognize the eigenvalues. So the eigenvalues will be 2, because it will always be lambda, lambda at the diagonal. Okay? So lambda equals to 2 and B must be equivalent to identity times the J matrix, which is B itself, times the identity inverse is still identity. And that's it. Okay, so this is IJI inverse, which is just IJI. Right, because B is J itself, what? Okay, so it implies that P must be I. If B is J, right, there's no choice. P must be I. Okay, and of course you can verify this yourself by going through the standard process. Okay, which I will not. Can So therefore, what's E to the B? Any questions? So last part, E to the B. So E to the B must be P times E to the lambda, E to the lambda. Then this one, right, you differentiate E to the lambda. So you also get E to the lambda times P inverse. But your P is I, what? So therefore, it's going to give you I times E to the 2, E to the 2, E to the 2. Because the lambda is 2. Times I inverse, which is just the central matrix itself. Because I times anything is I. Is that right? So similarly, the same approach extends to the cosine of B. So the cosine of B, right? Same thing. Cosine of B must be I times cosine lambda cosine lambda 0. Then this part must be the derivative of cosine. So this one must be minus sine lambda. Okay, because this one we mentioned during the lecture just now. The top right is the derivative of the function in the diagonal. So this one, so you have to d lambda times cosine, d lambda of cosine lambda. Okay, then you multiply by I inverse. So the answer is really just cosine 2. Then cosine 2. And this one is minus sine 2. So you can see that we can define the functions of a defective matrix easily. Any questions? Right, if you have no questions, then let's call it a day here. Okay, so we're only left with the past year paper question. Hopefully you can try that out first before I'll go through on Monday. Okay, after the quiz. Right, so the past year question is not part of the scope for your quiz 1. Thank you.
When is the